Thanks everyone for coming. Thanks to everyone here in the audience. Thanks to the organizers for making this happen. I'm going to talk about IPFS today, and specifically the practical parts, because IPFS technically is like a Web3 technology, right? And that's a lot of buzzwords, a lot of positive or negative thinking for thinking of IPFS or Web3 in general. So I want to do this talk to really talk about the practical parts of IPFS, not just a lot of buzzwords and excitement that may or may not mean something real. So my name's Cody ZUSCHLAG. I'm a staff developer relations engineer at Nearform. I also teach at the local university, University of Savoie-Mont Blanc in Annecy, so in Haute-Savoie. Feel free to scan the QR code there if you want to talk some more on any of the social networks, learn more about me or Nearform. I'd love to talk about IPFS or some of the things I do at Nearform or open source. Those are all subjects I'm really passionate about. I'll put the QR code up at the end in case you change your mind and decide by the end that it's worth talking. Also, reach out to me for questions. I'll be at the conference the rest of the day. We can talk after this. We can talk later today. I've lived in France for a long time, so I speak French too. So English, French, doesn't really matter. I teach in French also, so we can do all languages. No pressure. So IPFS, what is it? Well, it's the InterPlanetary File System. That's it. We can go home, right? How many people have used IPFS or know what IPFS is? A couple. Oh, a few. Okay, awesome. Glad to see that. So if I was going to wrap it up into one sentence for everybody else, it's a peer-to-peer distributed file system. It's content addressable, and it's for immutable storage. So now the talk's really over. You can go home. Now we're going to go into a little bit more detail, of course. And like I said, it's Web3, but I'm not really here to sell you on Web3 being the future that's going to save the world. But we'll talk about it a little bit. So at the core, it's storage, right? It's a file system, so it's for storing files. It's storage. I'll apologize now. I was trying to come up with a good metaphor for storage. The best I could come up with was like chipmunks storing stuff in their cheeks. And I know we all love cute animal pictures. I love cute animal pictures, so there's going to be a lot of chipmunk pictures during the slideshow. So storage, and not this type of storage, right? This is one type of storage. That's not what I'm talking about. I'm not talking about a place where you can put your furniture when you're moving or going on vacation. More like this type of storage, right? Computer storage. Maybe it's in a data center. Maybe it's on your phone, maybe it's on your desktop computer, your laptop. This type of storage is what we're talking about today. So before we talk about IPFS and how we can use this for storage in our applications, let's do a brief history of storage and computer storage. So same chipmunk, but in the past, so it's black and white. So if we go back to the beginning of time, when there were still dinosaurs, this was like the first hard drive. Although there's a debate if it was really a hard drive because the platters weren't really hard, so was it really a hard drive? But we're going to call this the first hard drive from IBM. Hold a whopping 5 megabytes of storage. That guy's pretty proud up there, pointing at his thing. But it's huge, right? This is something you'd have to connect to a mainframe computer. So you have to like a special room where you have like special air conditioning for a giant computer. So it's centralized. Like that's what I want to talk about. That's the theme that I want to drive away here. Like this is centralized storage because you can't put that thing under your desk, right? And of course, as time goes on, we make a lot of advancements. So we can fast forward 25 years, no longer dinosaurs. And boy, we've made a lot of progress, right? This hard drive is really portable. No, it's still huge, right? You still can't, this is still centralized storage, right? This is something inside a mainframe computer. You're not going to stick that thing under your desk either. They did make some progress in how much storage, right? We're at 250 megabytes, 1979. I don't know the manufacturer of this hard drive, but just to show, progress is happening little by little. This one's really technically a hard drive. And there's more progress, right? So as time goes on, hard drives get smaller and smaller. I've never seen that hard drive in the back, that huge one. I've never seen one like that. The 4 smallest ones I've seen and I've used in my own computers. But those first 2 big ones, right, it's still pretty centralized storage, right? You're not going to have that huge hard drive in your desktop computer or your laptop, right? It's still centralized. But as things get smaller, we can start to see things getting decentralized, where I could carry that around in my pocket. Once upon a time, I'm old enough to remember like using like a classic iPod that had like a little hard drive in it, a little 2.5-inch hard drive. So that was like more distributed because I could, or decentralized is the word I'm looking for. It's more decentralized because I could take that to my friend's house and we can make copies of MP3s. And not that we ever did that, but we could have if we wanted to. So it's starting to get portable and starting to get a little bit less centralized, decentralized. And if we look at portable storage, it's the same thing, right? I'm old enough to remember using the floppy disks on the left of that slide. And you would install your software, and of course, you couldn't just have one floppy disk. Like you'd buy some really cool game or some really cool word processor from the 90s, and it would come on like 20 of those disks. So you'd walk around with boxes of these, and you'd bring them over to your friend's house, and he'd make copies. Maybe he'd share them with 2 of his friends. So it's decentralized, right? It's spreading around. We can carry it in our pocket. We can share the data. It's becoming decentralized. So it's kind of this cycle, right? We went from something really centralized, storage, data centers, to kind of decentralized storage, portable storage. Same thing with CDs or DVDs. Not that I ever did it, but we could have copied CDs, right? Buy a CD, copy it, give it to your friends. That was pretty cool because it's digital, so the copies were perfect. And then if we look at, solid state storage, SD cards, pen drives, it's getting smaller and smaller and more portable and less centralized. It's getting more and more decentralized. And the same thing's happening with solid state technology, right? Smaller and smaller and smaller. I guess compact flash isn't technically an SD card, but we can see as time goes on, it just gets smaller and smaller, all the way down to that micro SD card on the right that we still use today, right? In our telephones or your Raspberry Pi. And this portable storage is decentralized. We can share that with other people. So the point that I want to take away from this little history of storage is like there's this cyclic evolution where we're going from something really centralized around mainframes to something decentralized, right? Portable storage. And I think the same thing's happening now, today, in 2023, because the cycle has repeated itself. We've gone back to something really centralized if we're thinking of cloud storage. So whatever your favorite provider is, maybe you're developing with AWS S3 buckets, Google Cloud Storage, iCloud, your iCloud storage. It's something centralized. It's not centralized physically, right? Because they might have multiple data centers, but it's still one provider. It's still, if you're using S3 buckets or Google Cloud Storage, you could pay for a multi-regional bucket, or maybe you have your bucket in one region. So maybe that's multiple data centers, maybe not. So if that data center disappears, it's still centralized. You could lose your data maybe. And now I think if we look at IPFS, this is where it comes in. Like we're making another lap around the cycle to something less centralized, decentralized, peer-to-peer, Web3, woohoo, IPFS. So the theme of these slides here is to show as time goes on, as history repeats itself, we're going in these cycles. Centralized, decentralized, back to centralized with cloud storage. And now I want to challenge us today to think of IPFS as the next evolution to something less centralized. So I'm really stuck on this point of centralized and decentralized. One last slide on that. Centralized, had to put a little graphic up here. I'm visual, needed that. So whether that was that giant hard drive, that giant mainframe, I'm also old enough to remember not using, but as a child, visiting a university where parents were working, and they had like a mainframe computer in the basement, and then each of the offices had like terminals that would access the mainframe. So that's that centralized, or maybe that's your cloud storage provider, because you're building your app on a cloud storage, or on a cloud services, you're building a cloud-first architecture. It's still centralized, right? Now, if we look at the right-hand side, the decentralized, that could be those floppy disks that you go and take to your friends, and they could share it with 2 other people, and those people could share it with 2 other people. And there's some interesting advantages, disadvantages also, to using something decentralized. And IPFS works that way, right? That's like a peer-to-peer network where if one person downloads a file who's maybe geographically close to you, ideally that's the case, and then you can download it from them, and then people close to you can download it from you, and suddenly the network works much different. And we can think of that also some interesting things about the load on the network, maybe the cost of hosting a giant server in the center that has to be able to scale to work at the peak times when everybody's trying to access a file, whereas if it's distributed, maybe you have to wait a little longer for it to come, but it's going to distribute, and you don't have to run a giant network, a giant server in the center. It scales a little bit more horizontally rather than just vertically. So distributed storage is really what we're talking about, whether it's centralized, cloud, decentralized, IPFS. That's really the point that we're talking about. So if you want to go and get technical, really talking about a distributed data store. Typically, we're talking about distributed databases, but IPFS is really a file system, so it's not just a database, but you could build a database on it if you wanted to. And so the technical definition of that is data that's stored on more than one node. Often that means it's replicated, but it's not a requirement. So replicated meaning you have like 2 different nodes, 2 different data centers, it's getting copied to different places. Or if we have a peer-to-peer network, I'm copying data from another peer, so we're replicating the data. And IPFS is a little bit more dynamic than that, but we'll talk about that in just a second. So right now I want to talk about distributed storage or distributed data stores. And there's been a lot of research around this domain, right? Because this is kind of the future. We live in a small world, I guess, and with technology, it's getting smaller. So a lot of effort, a lot of research has gone into this. And one of the things is the CAP theorem, which is something really specific to distributed storage. If you're like me, the first time I heard this, I was like this chipmunk. What? CAP theorem? So CAP theorem came from this dude, Eric Brewer. He says he kind of created it in 1998. He developed it a little bit further in 1999 and 2000. He still talks about CAP theorem today. And he was, or is, a professor at the University of California, Berkeley. He's currently, well, I know there's Google people in the room, but he's currently the Vice President of Infrastructure at Google. Maybe that title changes, but last I checked, it was that. He also helped roll out USA.gov, so the first government website in the United States. So he's got a pretty big resume. His CV is pretty long. He's got some credentials. And he came up with the CAP theorem. Basically, he said if we talk about a distributed data store, there's like 3 sides of a triangle. So imagine a triangle. I'll get the other 3 sides on here. And on one edge of the triangle, we have consistency, where we say for every value, for every shared value, there's a single result. So technically, we mean every read receives the most recent write, or an error. I'm not saying that we have to get a response back, but either it's the most recent data or an error. So saying if somebody hits a server in North America, they're going to get the most recent data. As somebody who hits the server in Europe, they're going to have the most recent data. So consistency. Every read receives the most recent write. Now the next edge of the triangle is going to be availability. And here he's thinking about 100% availability for reads and writes. So a little bit more technically, every request receives a non-error response. And there's no guarantee, if we're just talking about availability, there's no guarantee that it contains the most recent write, just that you're getting a response. So availability, we're always going to get a response, no errors, is one edge of the triangle. And the final edge of the triangle is partition tolerance. And here he's talking about tolerance to network partitions. So 2023, I might have reworded this, but then he wouldn't have the cool acronym CAP. But he's talking about like network stability, network tolerance, so tolerance to problems in your networking. So the technical definition, the system continues to operate despite arbitrary number of messages being dropped or delayed by the network between nodes. So between nodes that are replicating data or sharing in the distributed storage. So what his theory was, what he said, you can only have 2. You have to compromise on one edge of the triangle. Like we can't have all 3 of these. There's something contradictory about having all 3. So he said either you can have availability and consistency, or I should say consistency and availability, the CA, and you have to give up on partition tolerance. You can't be resistant to network failures. Or you could have availability and partition tolerance, and you have to give up on consistency. And of course, yeah, I'm going in a circle here. you have consistency and partition tolerance, and you have to compromise on availability. And he took it a step further to say, but you know what? If we talk about a wide area network, so a network that's spanning a big part of the geographical area, so a part of the world, thinking like the internet probably, right? He's like, honestly, there's always going to be network problems, right? We have to have network partition tolerance. We have to have network partition tolerance. So he said, honestly, you can really only have these two. Like you always have to plan partition tolerance into your distributed data store. So the compromise is either going to be, you're going to compromise consistency and have 100% availability and partition tolerance, or you're going to compromise availability and have consistency and partition tolerance. So back in 1998, this is what he said: impossible, you only have two, and the way the world is we have unstable networks, so you can't have consistency and availability because the networks just don't provide that. So this was like his big theory. This was the point that he was trying to make, that we can always assume that the network isn't always stable. So if we want to now switch gears a little bit to talk about some of the cloud storage, some of the cloud services that try to solve the CAP theorem problem, right? So that was back in 1998. It's now 2023. So things have changed a little bit, right? And the cloud providers are trying to solve this problem. And Google's come up with a pretty clever solution called Cloud Spanner. I tried to throw some of the Devoxx graphics in here, so I don't know, it's not really fitting, but there's one Devoxx graphic. They gave us some cool graphics to put in here. So surprise, surprise, Eric Brewer helped make Cloud Spanner, right? He wrote a white paper on CAP theorem and how Cloud Spanner solves the problem. And so it's just one of the different cloud providers that are trying to provide a solution to the CAP theorem. And basically what he's done at Google, or not him specifically, right? It's a lot of amazing engineers. They said, you know what? We can solve the network partition problem because we own the network between our data centers. It's not running over the public internet, right? They have their own lines, their own network. They own the network infrastructure. And he said, we can build a super resilient network infrastructure that's 99.999% network tolerant, like available, that 5 nines worth of availability. He said, if we do that, we no longer have, partitioning is nearly eliminated. So we're no longer bound to building in partition tolerance into our service, and we can provide that sweet spot for the consistency and availability. And that's what Google Cloud Spanner does. It's kind of like a SQL-like database that's distributed, and it attempts to solve the CAP theorem problem to 99.99% of the time. So this is one solution that we could have for CAP theorem. And it's a clever one. And like I said, Eric Brewer, he wrote a white paper about this. I'll put a link up at the end of that white paper if anyone's kind of interested in that, in this service. But the link's really long, so honestly, if you just search CAP theorem Cloud Spanner, it'll be like the first Google result is this white paper that he wrote. So this is one way that we could solve this infrastructure challenge, right? But I'm here today to challenge us to think maybe there's another way to solve it. And maybe IPFS can solve this in a different way, with some different positive attributes and negative attributes, some advantages and disadvantages, just in a different way. So let's take a little time now to deep dive. I'm not going to go too deep. Light dive into IPFS and what is it. So I've just stole 20 minutes of your day, and we haven't really talked very much about what is IPFS, nor the practical parts of IPFS, but now we can do it starting now. So IPFS, it's decentralized, right? It's not owned, nor is it running in your favorite cloud service. This is a decentralized technology. For better or worse, there's definitely some advantages, and there's definitely some disadvantages to that. I'm going to be perfectly honest, but it's a decentralized technology. It's distributed. So it's distributed over multiple nodes. It's a distributed data store, not necessarily completely replicated on every node, but that wasn't a requirement to be distributed. And you can download and you can distribute files. so you're also distributing yourself. So multiple ways to think of the word distributed. It's peer-to-peer. There's no centralized server involved, and it's pretty similar to, it's actually quite similar in technology-wise, with some subtle differences, to BitTorrent. Maybe you know what that is. You don't have to raise your hand. Not that I know what that is. Not that I was, downloading movies. But you could have if you wanted to, and it's a pretty similar technology. The way that it works, the way that the peers communicate. So we've probably used that before. It's content addressable. So I'm going to talk a little bit more about this in the next slide, but basically you take your data, you put it in what they call an archive, and then you hash it. And the result of that hash, which is like 256 characters or something, is the address to your data. And this is really cool because you can also validate your data when you get it, that's actually the data that you want. You don't have to rely on any third-party authorities to tell you, oh, this is actually the thing that you're looking for. I'll deep dive in that in just a second. It's immutable. And this is kind of tied to the content addressability, is that, if the data changes, that hash changes, so you're no longer, once the data's out there, it's out there, right? If you ask for this hash, and then you get the data, it has to be that hash, or if it's not, it's invalid data, and you'll throw it away. And obviously, don't put anything out there that's sensitive to you, right? Because it's a peer-to-peer network, it's going to get shared. Once it's distributed, it's out there, you don't really have control over it. Of course, you could encrypt your data before you put it into this public network, right? We already use encryption today, so it's not that it's insecure, but if you're going to go and play around with IPFS, probably don't want to put some sensitive data out there on your first try. It uses distributed hash table technology, so it's using a hash table, which is those hashes to the data, and it's not replicated. The entire hash table isn't replicated on every node, just the nodes where it makes sense. So if anyone here has used BitTorrent, don't have to raise your hand. You probably remember your client connecting to DHT servers. Well, it's the same kind of technology, right? It's distributed hash table servers trying to get parts of the hash table and figure out where it would need to go to find the parts of the hash table that it doesn't have. So IPFS kind of works in the same way. Buzzword alert, Web3, woohoo. So we can all go home. We found the solution to all of our problems, but it is decentralized. It's not tied to any particular cloud provider. It's distributed. It's democratic. It's open source. Got my open source shirt on today. So it is a Web3 technology. I'm not going to debate what is Web3 because that's just marketing, right? But it is. If we can check off all the boxes of what Web3 is, and IPFS falls in there. It uses directed acyclic graph for storing the data. So when we build that archive of the data that we want to store, it might get chunked into multiple parts and then distributed out to the nodes. And when you're trying to gather that data, you're going to start at the top of the graph and follow the arcs between the graph and get all the data as you traverse the graph. So you kind of think of that as like a folder structure, right? You're going to start at the root and then traverse each directory, collecting all the data. Although you started with an archive and it's just kind of chunked, it's not saying you're putting each file in a different part of the graph, but it uses a directed acyclic graph technology. So that's kind of IPFS in a nutshell. So let's deep dive in a couple of those aspects. The first one that I already touched on was this idea of being content addressable. So if we look at Web 2, buzzword alert, we live in Web 2. In Web 2 technology, we all know and we love URLs. So here's a fictional URL. I just made this one up. Squirrels.com/peanut. It's not really a squirrel, it's a chipmunk, but we can imagine that this photo lives at that URL. Now, if we want to go and download that photo, we have to rely on a centralized authority for the host name, right? A DNS server. So when I look up squirrels.com, I'm going to go ask the DNS server, what's the IP address? What's the address that doesn't change for the server where that data is located? Or it can change, right? Like the host name itself is an abstraction. So today it could be at one server, and tomorrow it could be at a different server, or in 3 months, it could be at a different server, right? The host name itself is an abstraction. And we have to trust that centralized authority. Like, we have to trust the DNS servers that they're sending us to the right place. That's how we live and we work today when we're talking about Web 2.0. And furthermore, the entire URL is an abstraction, right? The path, the /peanut, is also an abstraction. So if you've ever coded a web server, I assume most people here have, you know that you would define routes, and you can serve whatever you want at that route. You could serve fixed static data that doesn't change, or you can serve dynamic data, right? The URL itself is an abstraction layer. So if you ever coded a web server, you know exactly what I'm talking about, that it could be one image today, and tomorrow it could be a different image, and in 6 months it could be a completely different image. So we've already seen 2 layers of abstraction in a URL. We have to make a lot of assumptions, and we have to imply a lot of trust. And same with HTTPS, right? There's certificates, and we can follow the chain of trust of the certificates back to an original signing authority. And at some point, you just have to trust that signing authority is trustworthy, right? There's some implied trust just in HTTPS itself. So that's the world that we live in. And there's some advantages to that, right? Because abstraction layers let us do things dynamically, which is pretty cool, honestly. But it also means we have to make a lot of trust, a lot of assumptions, and the data could change. Now, if we look at IPFS, we have content identifiers. This is where I was talking about that hash. So here's like an example of one. It's actually much longer than that. I put 3 dots in there to make it fit, concatenate that onto my slide. It's actually much longer than that. So /IPFS/ some long hash. And what we've done is that hash is derived from the content. So this is really cool, and I already touched on these points, but we don't care who hosts the content, right? We're going to ask the peer-to-peer network, go get the data at this hash, at this address, and give it to me. And once you collect that data, you can hash it yourself and make sure it matches the address that you're looking for. So there's no implied trust, right? You can do it yourself. So this is really part of the interesting distributed part, the peer-to-peer part, kind of that Web 3 part, right? Like, there is no, you don't have to intentionally trust anybody when you're accessing IPFS data. Now, this is cool because if I access that data today or in 2 months or in 3 months, it's always the same data. And that's really cool. But there's advantages and disadvantages to that. I'll talk about this in just a second, but you could host websites with IPFS. But if your content changes, the address is changing, right? So you still need some sort of abstraction layer if we want to have like websites that could change over time, right? And there are services that do this. So there's advantages and disadvantages to using that, but that's one of the things that makes this an interesting Web 3 technology, is we're not relying on a centralized authority to give us the trust that we want. So let's talk about another thing related to IPFS, which is gateways. And another buzzword alert, we call gateways Web 2.5. Kind of in between. That's clever. Whoever coined that wasn't me. Basically, a gateway is like a bridge between those Web 2.0 URLs that we all know and we all love that we use today, and things like IPFS. And specifically an IPFS gateway is that bridge to IPFS. So it's going to host a server, an API that uses URLs like we all know and love, like any other API that we use today. So you can access that in your applications today that are built on HTTP and used to using REST APIs or whatever your API technology is. And they host a server that's connected to the IPFS network. So you can access data. In the URL, you can provide that content identifier, and they can go and fetch it for you from the IPFS network. This is kind of cool. I'll give a couple use cases in a second. Here's an example of one, web3.storage. They're a storage provider, kind of a cloud storage provider, but it's a Web3 cloud storage provider because they're storing your data in IPFS. So it's immutable, it's content addressable, and they have a really cool URL scheme where you can just put like web3.storage at the beginning of your URL, and then /IPFS/ the ID of the data that you want to get. And you can use this today. They have like a pretty nice free plan if you ever want to experiment with that. Maybe move away from your favorite cloud storage provider today for personal storage. A really cool project. So that's technically a gateway because they're storing it in IPFS for you, but you can access it with Web 2.0 URLs. Cloudflare, they have IPFS gateways too, so you can get any data out of IPFS that you want to. There's others out there. You can Google IPFS gateway. There's a million of them that exist. And this is pretty interesting technology if you just want to take a small step towards IPFS, but maybe you're not quite ready to host the IPFS node on your machine. I have my little MacBook Air here. I've run IPFS on this. It's actually really simple, right? It's not that big of a deal to run an IPFS node. But if you weren't quite ready to make that step, you could explore gateways. It could also be interesting for like portable devices, like your phone, right? We have Android, iOS. Well, iOS doesn't let us run background tasks. So that's probably why you've never seen like a good BitTorrent client on iOS, right? Because it's not running all the time. It can't run all the time. Apple doesn't let us do that. So using something like a gateway is an interesting technology because we could access the IPFS network when our application's running without having to have a node that's running all the time. Now, even if or when, who really knows, Apple would let us run background tasks, the portable phone's still a difficult place to run a peer-to-peer network because the network's not always stable. You might be in places where you don't have access to the network. So gateways are an interesting place for portable phones. Also, I talked a little bit about taking that stepping stone and being sure that your data is there. So if you put data on your IPFS node and nobody copies that data, when your node goes down, your data's gone, right? Like nobody's replicated your data. So there's things like pinning, we call it pinning services, but you can pay, or there's free plans to a node, like copy your data, pin it, so that's always there in the IPFS network, even if your node goes down. So I just wanted to say that, especially around portable phones, it'd be interesting. You put your data in IPFS and then use a pinning service to make sure your data stays there if your phone disconnects. So why? Why would you want to use IPFS in your applications today? That's probably why most of us are here. So let's talk a little bit about that. I came up with a list of use cases, and these are just kind of some wild, crazy ideas. There's plenty more ideas. So go and you can search, you can type IPFS ideas, or how can I use IPFS in my application? Just like kind of get the wheels spinning, the gears turning a little bit. I wanted to give some ideas of how you might be able to use IPFS today in your applications. I already mentioned website hosting. So this is one interesting place. Because it's immutable, and because it's distributed, it'd be kind of interesting because you don't have to pay for like a centralized server or your favorite CDN to distribute your data. It could go out in IPFS. As I already mentioned, if you want to have dynamic URLs, you're going to have some sort of abstraction. That exists. You can go and Google IPFS website hosting. It exists today. People do this. Some really interesting projects around it and solving that kind of DNS dynamic piece to it. There's projects that do that too. Thinking about distributed package management. So I do mostly Node.js development, JavaScript development today, so NPM is kind of my thing. But what if in like my package JSON, instead of storing like a version, what if I stored the hash of my package? It's fixed, right? It's immutable, can't change. No longer really reliant on a centralized service like npm to host the right data. I'm always sure that the data that I get is what I'm asking for. There's some interesting concepts there, right? And if I update the version, I just change the hash. This could work in an interesting way. We could kind of solve some of the challenges that we have around supply chain security if we were to use IPFS for distributed package management. There's projects that are kind of working on this, but just to give some ideas. Another one might be storage of like publicly accessible documents. So thinking like land deeds, like who owns property, like that's public information, at least in the United States. But you have to go down to the city hall, or in France, you got to go to the mairie or the archive to get some documents. What if that was all hosted in IPFS? It's immutable, right? You can't change it. You have to have some mechanism to find the address to the data that you're looking for, but we could build that abstraction, right? So I think this could be an interesting way to distribute public information. Why isn't this happening today? Why are we relying on giant data centers to host this data? I think this is an interesting idea. A colleague of mine came up with an idea he called distributed gaming, which I thought was, probably clever marketing. He was a salesperson. But basically, he was saying, imagine if you had a game where you build things, right? And then you could share those things that you built with other people. And what if that used IPFS? What if it used a peer-to-peer network so that, if your thing goes viral and a whole bunch of people want access to that thing that you built that you're distributing in your game, it doesn't have to go to one centralized server and then get, replicated geographically. What if you could distribute that with IPFS so that, somebody in your region could download that token, that object, and then you could download it from them, and then you could share it with 2 other people. There's a couple advantages to that. First is the load on the server, right? You don't have to have a server that's scaling vertically. It's like the network's distributed, so it's being shared horizontally by nature. So it could be an advantage cost-wise, right? It would cost you less to host that server. And also maybe there's an advantage in speed, because if you download it from a neighbor rather than from some distant data center, maybe, to be proven. NFTs. So buzzword alert again. I'm not here to sell you NFTs or pictures of apes, but you could. And surprise, surprise, most of the NFT services are using IPFS on their backends. If you go and look at the talks, look at their technology, they're usually using IPFS, and they're providing a pinning service. They're guaranteeing that your archive, your data in IPFS will stay there, so you can go and validate that your ape picture matches the hash of the one and only original ape picture that exists. So IPFS is a good match for NFT services, for better or worse. So that's just a short list of possible use cases. There's plenty more you could go and check out. Just wanted to kind of get people's imagination working. Looks like I have about 7 minutes left. But I'm a big fan of open source. Got my open source is art t-shirt on today. Actually, I have a whole nother talk just about open source and how that can bring value to an enterprise or your organization, and how that can differentiate your organization from the competition by investing in open source. If you want to talk about that, reach out to me, scan that QR code in the end. Love to talk about that some more. But IPFS is open source, which is a really cool differentiating factor for IPFS versus your favorite cloud provider. And I want to talk to you about some more history, a book that was written in 1999 called The Cathedral and the Bazaar, written by Eric S. Raymond. And he was writing a really popular tool about mail. I don't know if it was send mail. I'll have to check the name again. It just escaped me. For the Linux project. And he came up with this concept. There's the cathedral and there's the bazaar. And he basically said that when we're developing, he's talking specifically about open source, there's 2 approaches. There's a top-down approach and a bottom-up approach. And the cathedral is that top-down approach where the source code is available, possibly, on every release. So it's still an open source project. But there's a select group of developers. There's only a select exclusive group of people that are developing that code. So even though they're releasing the source code, it's a small group of people that have access to it. And this is an interesting idea. I think this was Emacs back in the day. So if you're a real geek, you probably use Vim now, but Emacs was kind of a competitor for a long time. Versus the bazaar, which was more like the Linux kernel, this bottom-up approach where the code is developed on the internet. Today, that's probably going to be GitHub or GitLab if you want to find an alternative. And it's developed in public, right? You can go and create a PR. You can go and create an issue. You can go and read the source code yourself. And his basic premise was, you might have heard this if you've researched open source yourself, is that given enough eyeballs, all bugs are shallow. That was the point that he was trying to make when he wrote this book. And the idea was the easier the code is available for the public to do testing, for the public to scrutinize, for the public to experiment, the more rapid all bugs will be discovered. Not just the specific bugs you're looking for, but all bugs. Of course, this kind of depends on the popularity of your project. And we could talk about legacy code if we want. I have another talk on that. But a legacy project, really important. There's only a few devs running it. Is that really secure either? There's plenty of that in the ecosystem, especially around JavaScript, packages that we take for advantage. But if enough people are using it and looking at it, the bugs become shallow versus that cathedral time, that cathedral code, where you have lots of time and energy spent hunting for bugs in the cathedral. So he was really, driving this idea, and it was the Linux kernel at the time, that code should be developed in public, in open source. And IPFS is just that. IPFS is an open source project. You can go and contribute. You can go and make it better. You can go and see how the security works. You can go and, there is a community, a large community around IPFS. I encourage you to do so. It's actually really cool. And I think that's another differentiating factor if we're looking at that cycle. Back to the CAP theorem, right? We're trying to solve the CAP theorem. And on that note, there's a battle taking place right now. And the battle is trying to, take distributed storage, a distributed data store, how we're going to, share data between multiple nodes, and how are we going to solve the CAP theorem problems, right? The challenge is that CAP theorem, it's a theorem, it wasn't a law, right? And so we're going to solve it, right? And there's these opposing forces trying to solve that, the challenges of the CAP theorem. How can we provide all three sides of that triangle? But we can take a centralized approach, or we can take a decentralized approach. And maybe it depends on your application. Maybe it depends on what you're trying to build. Oops, oh, too fast. We can take a cloud service approach, or we can take an IPFS approach, right? These are two different approaches to try to solve the same problem. And I apologize to my friends working at Google, they're in there, but you go and let someone else do it for you, which has some great advantages, right? Like, I don't care. I trust all the amazing engineers working at your favorite cloud service provider, or you could do it yourself and get involved in an IPFS project. So that's kind of the point that I want to leave you with today is there's two different ways to solve the problem. Choose what's best for you. Choose how you want to get involved. I'm not going to say that one's really better than the other. I just want to be really clear about that. I work at Nearform. They made this cool t-shirt for me, open source is art. We do like professional services, which is kind of a fancy way for saying consulting, but we're also really active in open source. We actually hire Node.js core developers. We have people working at Nearform that are on the TSC, the Technical Steering Committee for Node.js. So we're super active in open source, and we do consulting work. This is kind of a cool balance because we can go and geek out on open source projects and then apply those skills with actual clients, actual enterprises, actual organizations. So I like to say that we can walk the walk and talk the talk. And specifically around IPFS, we built what we call Elastic-IPFS. And Elastic-IPFS is, as I mentioned, it's a peer-to-peer network, right? You have nodes. And the challenge is if you're building a service and you have a lot of users, how do you scale your IPFS access? Because if you only have one node, you can only really scale vertically, right? You can only add RAM, bigger processor, pay for a bigger virtual machine. But how would you do that if you wanted to have multiple nodes? How could you scale horizontally? So they took the aspects of IPFS, of an IPFS node, and we implemented it on AWS. That's what the client wanted. And it's called Elastic-IPFS. It's super cool. It was architected by a colleague of mine who couldn't make it today, Paulo Insomnia. And it's infinitely scalable, right? Because we're building it on cloud services. And this is something really cool. So if you want to talk about Elastic-IPFS, come see me. I just kind of threw this slide together yesterday, but if you want to know more about that Google white paper on CAP theorem and Cloud Spanner, I put the link up there, which is horrible, so you can try to take a photo of that. If you just Google Spanner, True Time, and the CAP theorem, that's the name of the white paper. You can check that out yourself. And Elastic-IPFS is GitHub / Elastic-IPFS / Elastic-IPFS with a dash in it. Put my QR code up there. You can scan that. You can find all my links to the socials. Come and talk to me. I'm really 5 seconds left, so I probably won't take questions live, but come talk to me here afterwards. Look me up. If you want to talk about We're always hiring at Nearform. If you want to talk about jobs, if you want to talk about open source, if you want to talk about IPFS, Node.js, hit me up. Love to talk about any of those things. Thank you so much for being here. Have a wonderful rest of your conference, and talk to you soon. Thank you.